Welcome everyone to this first episode of Iron Middle in the year 2026. So we've missed one episode during the Christmas break, and I'm sorry about that because I literally just forgot about Thursday. It's still happening, but well, we are back. And I must say that I promised to figure out what is happening with like Twitch not working for some people. I wasn't able to figure it out. So yeah, it's kind of the fact of life that like, some of you will be able to see this live, and some of you will have to watch the recording on YouTube. Without further ado, let's get back to what we've been doing these past few episodes, and that is trying to refactor targetable query engine, not like, some kind of like big-brained giant refactor like we did with compaction a while ago, but just like, chipping here and there, trying to make like code simpler, less error-prone, etc., etc. And last time, our goal was to simplify Kiwi merge implementation. So inside targetable, we use Kiwi merge for query engine in two ways actually. So okay, I guess I should start diagramming here. Let me quickly, or maybe not so quickly, try to show this. So can I make this? Okay, yeah, this is it. So in the room, okay, yeah, probably it would be a good idea to also share my screen. Okay, yeah, now this looks correctly. So yeah, like targetable is a LSM tree, which means that the data is organized as a kind of like layered cake, where each layer in a cake is some amount of tables. And the rules are that, I wonder, do we have a rectangle here? Okay, yeah, this is much better. Yeah, so the rules are of this like layered representation are, first of all, inside each rectangle, we have a set of values that is sorted. Then inside a layer, all rectangles are sorted and disjoint. Across the layers, rectangles might actually intersect. So we might have k equal 92 here, and here as well. So this is valid. And in this situation, the rule is that we prefer keys and values in the area levels. So that is LSM. So when you want to learn what data is your LSM is stored inside your LSM tree, if you want to scan, what you actually do is that you read each layer left to right in sorted order, and you also merge the results. So let's say we have so K92 here, and here we have K10, and here we have K20. So the way you would scan through this layer is that you first yield key number 10 because that's the earliest key, and then you yield key equal 20 because that's the next key, and then you have two options for key 92, this one and that one, and you yield the one from the previous layer. So that is where key we merge comes into the picture. We are merging across the layers. Now, what I've seen so far was a single tree. So let's say, I don't know, like transfers sorted by transfer ID. The thing with queries is that you might want to scan several trees at the same time. So for example, if we want to find all transfers belonging to a particular account, in the one tree, the index tree for debit account ID, we would scan a set of account ID, transfer ID pairs sorted by account ID, so that we find all transfer IDs belonging to account. And we want to sort of merge that set of account IDs, that set of transfer IDs which belong to a particular account, with the actual set of transfers. So we have index tree, we have account tree, and then we like merge them together. And in complex queries, you actually might want to simultaneously look at the key different strings. So that is why we get keyway merge or keyway merges essentially. Now, let's go closer to what have been bugging us. And that is the fact that underneath the keyway merge is a rather elegant, simple data structure. Well, it's not like simple, but it's like relatively simple, called tournament tree, which implements keyway merge algorithm more efficiently than just like, you know, a heap. But given that the data, you cannot, but given that the data we are merging is on disk, we need to have like, you know, asynchronously pull the data. And that kind of like turns into like this ugly asynchronous interface where like, you know, this how complicated the keyway merge actually is, and this is how complicated it needs to be to accommodate all requirements of our actual implementation. So what we are trying to do is we are trying to tease those two apart. Okay, there is like usual for Twitch complaint in the chat that hey, like video is not visible. I'm not sure what's going on here. Some people are able to see my stream. Some people are not able to see my stream. It kind of like is there on Twitch eventually, but I have no idea what's going on here. So if someone is able to debug this and say like, hey, this is like a problem, it will be like much appreciated. But like my Googling like failed. Okay, so let's just continue again as usual. This all is going to be on YouTube. So like last time, we kind of like implemented the split, and then we bogged down into like a specific implementation, which is kind of like tricky. So I want to push that over the finish line today, but what I want to do first is to take advantage of the refactor that Toby landed a couple of weeks ago, where he removed stream precedence because we don't actually need stream precedence. So let's actually start with rebasing our work on the latest version of the code. And I'm going to do this in like rather uninspiring way. And that is, I'm going to just reset the code to the main branch. And then I'm just going to copy paste stuff back. Like, who needs complex iterations when you can just copy code in and out? So yeah, so we no longer need string precedence, and that is great. Okay, we don't need this. So I guess the first thing we'll do is that we will check if this thing is working at all. Because previously we kind of like, okay, doesn't work at all in some pretty horrible way. Okay, let's see where we are at here. Okay, so I guess last time my why we decrement contestant's name, this feels incorrect. Okay, no, this feels correct. So where we bogged down last time was in that in the fact that like this kind of like wasn't really important. So we kind of like can go into this while, and then we go continue, and then next time around our string peak like returns pending, and then we like roll around. But I think that one is actually fine because our pop winner is actually idempotent. In a sense that if we replace winner with the same key, then nothing changes. So I think that should be fine. And that looks correct to me, but yeah, okay, so this is this really is the case where I want to find the minimal example. So like how are we going to debug this? Are we going to stick with this example, or are we going to do something smarter and find a smaller case? Well, sadly, it's kind of like, okay, let's actually do this. Let's say that this is test we small and do some manual minimization. So let's see. If I can make this thing fail faster. And it seems I can. So any other ways to minimize this? Okay, so this one shouldn't be deleted. Okay, but this is also well, this is a different failure, but it's also interesting. Okay, this is still failing. Now let's see if I could make this. Okay, this still is fake. So okay, this kind of like feels like this should be our test for debugging. Okay, so let's see, where are we failing? Initialized. Contest ID does not equal node sentinel. What is ID sentinel? ID sentinel is max int. Okay, how do we initialize this? Distance count. Okay, this really doesn't make any sense to me, I think. There's no way they can be int max, right? Oh, haha, haha. Yeah, I think I see one problem. So okay, where your this happening? Load. Okay. This should fix it, hopefully. Okay, yeah. So we now fail for more interesting reason. Let's see. Unit. Okay, unit still fails. And it still fails on this three-way test. So let's try to minimize it again. Okay, so apparently I need 3 here. And they probably okay, this fails. And with 2 doesn't fail. Okay, it's kind of like funny when things fail at 3. Distance count. Competitor index. Aha, so I think I got it. So I think sadly we need to, so basically I think the code expects that contestants has enough length to be a complete binary tree. And not just an arbitrary slice. So it's kind of like should be something like this, sadly. this. Can I, like this kind of thing is sadly pretty sensitive. How do we initialize the tree? This is going to get so. Oh, I don't know. It's actually fine. So do we do assert or is ID constant if is ID sentinel, we assert that contestant ID is also node ID sentinel. Otherwise, we assert the order. Okay, that feels roughly correct. And okay, so we don't need this. We have to say okay, we need to check how this looked before. Well, I guess for like let's kind of count. Let's do super simple thing. Yeah, so I do want. Well, okay, no. Okay, so I want to say that contest count. Okay, and then for the rest of them, we assert that is okay, yeah, this feels correct. So this is now just contestant count. If contestant count is 0, okay, I've lost. This is supposed to still be so then we pass all here, but pass contestants, pass contestant count here. Okay. So it actually needs to be U16, right? U16. Okay, yeah, this feels correct. And now, okay, yeah. So now we have expect output and okay, so it seems like we actually work. Let's see, Fazen. Okay, yeah, Fazen. Fazen, of course, immediately found a bug. Should we just go and implement minimization here? Like, really? Maybe we should. Well, okay, no. It's going to be hard to implement minimization here because or maybe not. It actually fails reliably. So what do we do here? Okay, there's really like this constant struggle. Whether you try to minimize or whether you like try to write automated minimizer or whether you try to find a unit test. Okay, let's try to. Okay, this is. Okay, yeah, I think because this is like Iron Beetle, and because we are free to do whatever we want to do, let's actually go on an adventure and try to implement a simple um, minimizing puzzle, because I'm not really happy about debugging this. Well, okay, now before, let's maybe we do have like one minimizing puzzle, and that is Exhaustigen. So let's maybe try first with Exhaustigen, and then we'll see if we need a real puzzle. But before we could try with Exhaustigen, I really want to like simplify tests, because I kind of like don't like really love this. Like, why do we need all those types? Okay, so we actually like, do we need type signatures here? We do not, in fact, need type signatures here. Okay, so let's actually just go and kill those type signatures, because they are hugely distracting to what's going on here. Okay, right, and we probably could do the same here, right? Okay, and can we do this deeper? Okay, yeah, we actually can fully get rid all this entire thing. Okay, this is already better. Now, do I want to specify so what bugs me about this test is that, like, we write this key manually. Like we write the expected value manually, and it feels like we should be able to just figure this out automatically. So I bet in the fuzzer we actually have code to figure out what the result should be. Okay, so can we do can we have merge naive value so fast as context? Okay. Duplicates. Merge. So what is expect buffer? So what I'm trying to do, okay, let me explain myself. I want to write minimal, I want to search for a minimal test case to prove, find, is it a debug test case? I don't want to manually implement the tests. I want to do a search. But if I do a search, I cannot actually write the expected function. I need to write a code which gives me expected function, and we already have this code in the fuzzer, and I want to lift it up into test context so that it is reusable. So context merge naive. So I guess buffer. So I want to or wait, what does it, what is version means? Test context streams. Okay, we already have streams. Buffer. How do we fill this thing? Okay. So we also need this thing here. And do we call this context? Context. Text. What is car? Streams max and what is streams? Okay. As value account account equals value account plus equal 1. Okay. Account value. So this is going to be value plus then order. Do I have okay no going to be all right. Okay. How do we deduplicate true? So deduplicate is actually true. Target buff account buffer target buffer. Okay, so in the fuzz we aren't actually parameterizing over direction, right? How do we set the text context here? PNG. Oh, we don't even specify this. Oh, we should be using direction here. Okay. Less than direction. Senden invert. Okay. Yeah. So now we set the streams. Okay. Let's do plus equal 1. Const buffer test allocator log value like I see this like Mr. Makita. You shouldn't be this is GPA. We use it as GPA. So let's be upfront and say, hey, we are actually using GPA here. Okay. Buffer. Key connect. Context. Direction and buffer. Shell. Okay, and then we demerge. Okay, let's see. So, and wait, this is right. Okay, no, okay, it is correct. Although it is odd. Assign to constant. Let's not make this a constant. Context direction buffer. What do you not like here? Okay, yeah, we should probably try this first. again. Buffer. Why we end up it makes zero sense to me. Okay, so actually what we want here is dreams, dreams Islam. Is going to be, yeah. Okay, so now I think it should work. Famous last words. So, okay, we don't actually. Is expect naive, expect now we only need actual here. Well, but we like it there. Okay, so okay, and this is, well, by the way, this is a common pattern. So whenever you have a set of unit tests and a fast tests, you will have inside the fast test some logic to test that, hey, this whole thing behaves correctly. That logic should also be engaged when you do unit tests. Okay. So now we could do finally test if we merge minimal const this context type. Let's say that we do 3 and then we need yeah, and then while gem. So what do I want to do here? I need to so I actually want to remove this for now, and I want to say t node sending, and then I actually want to pass nothing, and then like my thing. So it should be a slice of slices. So let's say that 3 equals to n, and increase 5. I don't think we'll need more than 5. So let's say that we have buffer, and that is n flat 0. Okay. How do I get themes? It's going to be n. Okay. And then for string count buffer index string count we generate some value here, and then we say streams index is buffer index string count index so this is then going to be a count a index. Okay, and we are going to merge strings. Okay, so let's see if the science works. Let's see if this gives us the bug. Minimal. Inspect and use function parameter. This is bad. Okay, yeah. Oh, okay. Actually, let's make this nullable and just see. Expect slice expect manual minimal. So I want to say no. Does it? Oh, okay. Let it be. Let it be with that. Include. Expect two arguments. Why? Because E32, I32, okay, and we want to try. It seems that our sense does actually work. Okay, so now let's see for strings s. Let's see what is our bug here. I think. Okay, so this is incorrect because we should also be sorting. Well, are we sorting them in Python? String keys. Well, yeah, we do. We do sort them as then. So, okay. This was premature. Index sort. Let's see. 4 arguments. We got 3. Why would you need 4 arguments? Slice context function. Oh, right. We also need to say that we are sorting 32. Okay, we want to slice them, so let's not mark that thing as a const. And that should be void and not an empty tuple. Okay, this works. This doesn't work. Okay, that is good. And let's see what's our test case. Yeah, this is our test case. So we could. Can we do this? Oh, no, it seems like we need at least 3. Well, actually, now that we've written this thing, I'm kind of like curious if we could actually run that on the main branch, just to check if this is, well, no, let's maybe do this after. Let's first do this mark. So this is our so we want to merge 3 things, and this are the 3 things we want to merge. Yeah, we want to test smoke. And this should use some pretzels. Okay, yeah. Twice is deeper. Oh no, it's not. I want a smell here. Okay, so what happens here? So it feels like when we load the pre, okay, so this is a nice bit of code. Yeah, I wanted to quickly finish it. We didn't finish it quickly, but I think we did do a couple of useful refactors of the tests, because what we did here, that is, unit test that also checks that the expected results matches what we wanted to match, and that our fuzzing is correct is good. So let's stop here. And the next time we are going to upstream our test improvements because I think those are important. And then after that, we are going to debug this data. But we did achieve one pretty remarkable thing. So again, we had this fast test. And I run this fast test, and okay, so now fuzzing doesn't work, but you remember that there was like, pretty large print out there. Like the fuzzing example was pretty tough. And then we run our Exhaustigen test, and that immediately found like a very small example where we actually do fail. Now that I think about it, it's actually kind of like bugs me. Why it prints, why it goes from just 1 to 3? Huh? Oh, okay. So it's not actually just 1. It's actually quite a few. So we'll start next episode with upstreaming this test, because I think this is like pretty awesome way how you could find minimal examples. Okay, so I guess that's it for today, and see you in a week at 5 p.m. UTC live on Twitch and on YouTube. Goodbye.